In this demo, we present ALLSTAR. ALLSTAR is a scheduler synthesis and testing framework which is developed at Northeastern University as part of our activities in the AI-RAN Alliance AI for RAN working group. But first, what is the MAX scheduler that ALLSTAR generates? The MAX scheduler of a 5G base station is the piece of software that allocates the physical resource blocks, e.g. spectrum resources, to UEs. The scheduler is usually the secret sauce for closed-source traditional vendor stacks. It is an industrial secret because it decides in large part the performance of the base station in terms of latency, fairness, and throughput. This creates a gap between the public knowledge, which mostly consists of simulation studies on a lot of scheduling algorithms, and over-the-air experimental studies, which have been historically hard to perform. There is only few over-the-air studies in the public domain. However, thanks to Open RAN and to the open-source 5G implementations of NVIDIA Aerial and Open Air Interface, we can now experiment over the air on a close-to-carrier-grade deployment using commercial O-RAN radios. Nonetheless, the scheduler is very hard to implement. It is stack-specific, usually intertwined with the control plane, yielding to a huge burden to implementation. ALLSTAR simplifies this process by automating scheduler synthesis with LLMs that generate real scheduling software based on literature and operator intents. Through this, ALLSTAR can test a large number of schedulers from the scientific literature and then recombine them into new schedulers based on intents. To achieve this flexibility, we leverage the new concept of Open RAN dApps. We implement the scheduler as a dApp, running in real time within the DU. This enables us to deploy the scheduler as a swappable piece of logic, concerned only with user plane resource allocation. The dApp framework enables us to meet the highest security and real-time performance requirements without compromising flexibility. Let's now deep dive into how ALLSTAR generates schedulers. ALLSTAR starts from research papers and technical reports. These report on existing algorithms that have only been tested in simulation. The first step is to take the paper, which is usually a PDF document, and to turn it into a markdown document ready to be ingested by a generative AI LLM. To do that, we use the NuGet OCR model developed by Facebook. Once we generate the markdown document, which is the only knowledge we will use to generate the algorithm, we can pass it to an LLM coding agent. This agent generates the code of the scheduler based on the paper and on its equations. The agent receives a prompt with 18 precise instructions on the scheduling dApp APIs and acceptable trade-offs. Simulation-based algorithms sometimes make unrealistic assumptions, which ALLSTAR knows how to correct. This gives us the first version of the scheduler code. However, no critical piece of software implementation would be complete without its testing suite. We propose a thorough unit testing framework which runs tests such as infinite loop detections and output validation, verifying that there's no harmful side effect to the new code. If one test does not pass, an error report is generated and passed to the LLM coding agent. This agent tries to generate the scheduler again, which then goes again through the unit testing pipeline. If all the tests pass successfully, we go to the over-the-air evaluation, with first a small-scale evaluation validating that we achieved decent performance with a few UEs before doing the proper performance test. Before the large-scale test, we also generate two reports, the design report and the difference summary. These documents leverage a second LLM agent which evaluates the code against the paper and the quality of the implementation. This allows a human operator to quickly verify the code and get pointers to errors. This accelerates the verification and correction process, enabling an engineer to validate a scheduler in a matter of minutes. Once this basic sanity check and testing is done, ALLSTAR moves testing to a larger deployment. This is where we use the infrastructure available at Northeastern University in the INSI Open 6G AI-RAN lab, including a set of Gracehopper GH200 in an OpenShift cluster running the NVIDIA Arc 5G stack. We also use a set of radios scattered around our campus and a set of Sierra wireless UEs readily available for testing. With this, we can perform extensive testing of the schedulers based on different radio conditions, different number of UEs, and different base station positions. The second type of report is performance tests. In this first figure, we see the similarity of schedulers in terms of average throughput allocation. Thanks to our repeatable over-the-air experiments, we can derive similarity metrics from identical experiments repeated 10 times per algorithm. The figure shows that, despite the claims in the literature, a large number of schedulers in the proportional fairness family have a very similar throughput profile. This indicates that there might be less difference between those than claimed in the papers. Some schedulers can, however, have subtle differences. For example, the proportional fairness with buffer scheduler, PFB, algorithm has a much better latency profile than proportional fairness, PF, as seen in the second figure on the right. This indicates that this algorithm would be strictly better to deploy than PF. We also evaluate quality of service focused schedulers. In this figure, you see 7 different schedulers evaluated on a 2 slices benchmark. The first slice has a 50 milliseconds delay target, while the other one has 500 milliseconds of delay target. You can see that out of all the tested schedulers, only a few can reach the required thresholds, opening opportunities for URLLC slice satisfaction. Beyond testing and benchmarking algorithms, ALLSTAR enables the generation of new schedulers through recombining multiple algorithms. In this example, we show ALLSTAR can leverage existing proportional fare schedulers along with a custom model for mobility detection. The operator can here input a natural language intent, which limits the throughput of static UEs. You see that as the UE moves, the scheduler gives it more resources, and its throughput immediately goes down when the UE becomes static. Thank you for watching this video. Please make sure to read the paper for more. Visit the Northeastern team at the AI RAN Alliance booth or on the Keysight booth for a different demonstration of the potential of agentic AI in the RAN.